Hey YouTube, it's Dimitri, and today we want to talk about my recent paper here on quantum finance here. So a little bit of applications of physics like quantum mechanics in finance here. I'm going to give you the big disclaimer. This is loosely related to physics. I have no intentions of actually trying to prove and derive and put together equations that align and match with the physics community in the world and quantum mechanics world. But a lot of the ideas, a lot of my hobby reading in the physics space just happens to spill over into the financial space. And when you read different topics from different fields, it's often hard not to link together new ideas here. So my recent paper is called Waves, Quantum Theory, and Retail Credit. And I have a bunch of these disclaimers in here talking about I have no intentions of making a complete theorem or proof to put together quantum mechanics into a financial space here. And I actually do not believe that financial markets behave like quantum systems and are kind of dictated by that and structured. There are people that do believe that. Again, it is labeled many things, this area of physics and finance and economics and everything. Some people call it, I think, like econophysics or something like that. Some people call it quantum finance. I'm just going to say it's quantitative finance, which is a massive umbrella of cross-disciplinary fields all coming together to study applications to financial markets here. So let's just dive on into this. I wanted to explain some of the kind of pieces and details to it. I will put a link to the actual paper in the description below. And a note here as well, as I scroll through and you go through the references, it is a little bit wonky when I hit load more. Like this is mistyped. This is supposed to be Jack Sarkeesian. His book is called Quantum Markets. And then again, Charles Torr got split into two different references. I don't know. It's SSRN's auto whatever thingamajig it does to do this. Anyways, that kind of bugs me, but let's just dive on into the paper here. So the abstract is really just a introduction to what is retail credit. Retail credit is going to be things like auto loans, mortgages. You can even use this for like credit card, which is revolving credit. But looking at some sort of financial loan to a consumer on the retail side of this. I go through a little bit of the history of explaining, like historically people would just take a sheet of paper and they would write on this sheet of paper, like income or, I don't know, credit score or some sort of metrics like, how many defaulted loans they have, balances, something like that. They would write it out and create what's called a scorecard. So essentially it'd say, okay, like your income accounts for, 40% of the decision if we're going to make you a loan or not, or the pricing if we use, pricing with APR. And they go through this process here and they would just manually go through the scorecard and everybody would get treated the same. But it was a really simple kind of dumb methodology because we didn't have a lot of technology at that point in time. Now, fast forward a bit here, computers, computation, data collection, all that. We started to see what are called scorecards, but now they're just done with a model. So logistic regression was kind of the standard to get going here when you do like probability of defaults, because probability is between 0 and 1. So you can use logistic regression to do that. And it would do something similar. You take a bunch of attributes now, like bureau attributes, like, like how many auto loans have you had inquiries on? So how many times have you gone and applied for an auto loan in the last, 12 months or 18 months or something? And the Bureau would collect all this data and we'd put this into a statistical model like logistic regression, and you would run this regression and it would auto weight all these different features, more or less like a really smart, statistically driven with business insights to come up with a much better scorecard. And then when you get into, again, more modern times now, we have machine learning really coming on. Probably the last 15, 20 years here in the finance space, which is much older than many other areas. But then they would use things like XGBoost, decision trees to go in and say, okay, consumers that look like this, again, based on all these credit bureau attributes, look alternative data sources, trying to figure out how do we group them so we figure out who's going to default and who's going to be a profitable loan, and then trying to use that to price and decision on if we're going to make loans in the process here. So this has really been the space. This has been the process. AI is coming on to see some automation. I would argue credit decisioning, credit scoring, pricing, all that has been automated for a long time now because we have data that's been automated to come in. It runs through a model, spits out a score, and auto puts back a decision. Most bank decisions, most finance company decisions are not made by a person anymore. It goes through this automated process through a model that statistically calculates, a bunch of different metrics of like probability of default, exposure at default, looking at timings when cash is going to come back and those sorts of metrics. And it makes a decision on it. So we've been doing AI with this. What has been newer though is the fact that we are starting to get more and more granular data. So there are companies like Finicity and Plaid, which are now saying, hey, if you want to make an auto loan or a mortgage, or you get a credit card, let's assess your credit risk and let us look at your bank account or your credit card spending. Let us look at these transaction level, transactions, like things like income and expenses, and assets, like how many assets you have, how many liabilities. If I could pull all of this in on a transaction level, I can look and say, wow, this individual has a reported annual income of X, but that could be outdated. It could be old. What is the timing of those cash flows as well? Are they on contract where maybe they land some big deal and get, $80,000 at the beginning of the year and they don't get paid until, I don't know, like July, August, September? That sorts of payments could be an issue and a risk, even if it's a larger sum, like $80,000, $100,000, $200,000. Timing, consistency, transactions, looking at consumer behavior on spending like expenses, all these sorts of things make the modeling better. But the argument of this paper is as the granularity increases, there is now actually a reason to move more towards a quantum-esque approach of going to be pricing out loans. And as I've read through physics, this kind of looks like a similar conclusion that we've seen in physics where, traditional mechanics was looked at. This is the trajectory of a ball. This is where it lands. This is how it processes. This is how things move. Fairly straightforward calculations, fairly straightforward movements. Then we start to get into atomic or subatomic particles. Again, big disclaimer, I'm not a physicist. I have no intentions of being a physicist, but I'm going to dumb these down as I understand them. But as you start to look at atomic and subatomic particles, you can see some sort of wave behavior. Now, when you get into the dual slit experiment where they fire the light through the splits, you can see there is actually a wave-like process or characteristic to light. So it actually does behave like a wave. This is what I'm kind of linking towards loans, where loans actually, when you look, for example, like at net income from a consumer. So they're making money and their net income's increasing. And then like all of a sudden your phone bill's due, your mortgage is due, you bought food at the grocery store, right? It goes down. And then as you go back to work the next day, right, if you look at this like, I don't know, seconds, minutes, hours, you can see your wages are going up. Again, your kids are at home eating your food. You have behavior that's driving it down because the expenses are increasing on that. So net income, I feel like in my mind, is a really easy process to kind of understand as a wave. Like you're always increasing and decreasing. Again, the way that we man-made contracts on like your mortgage is due on this date is something that hits periodically. So it somewhat naturally creates that wave. I would argue too that as we consume, we are not very linear in consumption. So we do not see like, I don't know, I eat $25 or $50 of food every day. Some days you're eating more expensive meals, less expensive meals, maybe you went out to dinner. There tends to be some sort of wave-like behavior in the way that consumers behave. So it's just something that I have noticed when looking at data and thinking through the process here. And so then there are a few ideas in the quantum space here, kind of these quantum mechanic ideas that I have read about and thought about, and then tried to link many of them back into the credit space here. Quantization, though, is interestingly enough one of the big issues within finance, and this comes down to that data granularity piece, zooming into like that transaction, minute, nanosecond level of looking like at net income, looking at expenses, incomes, looking at, for example, assets and liabilities, looking at these things like balance sheets, trying to figure out how the consumer is behaving and changing. One issue we end up facing, and we have faced historically, is typically I will get you our income in a monthly value. So when you look at monthly values, it tends to be quite linear. Like I'm hitting a specific point and it looks the exact same across time, or it looks like it has a little bit of variation, but there's no wave behavior in that. When you actually look at waves and quantization, if you start thinking about this now on that much more detailed minutes and second level, you start to realize like on weekends, you're probably not earning any money. So like net income, for example, has to be going down. That's just how it happens. And when we start to get transactional level data, it seems like we need to actually get more granular data. So quantization is when we take very granular data and we make it very high level to simplify it. So a good example of this is digital versus analog. So back in the day, analog was like a wave function you could think of. Information would get transmitted, whether it's like TV, radio, whatever. And it's a wave and it's a little staticky because the values of 0.5329 or something is coming in, but it's, the real value is just 0.5. And there's that little bit of noise here that we're picking up. And so we moved into a digital phase. And when we went to digital, just like traditional computers, we said, let's just round everything and have a system where it's binary. We have 0, 1. If something comes in, and let's say it's supposed to be 0.75, we'll just say it's 1, right? I'm oversimplifying this intentionally here for understanding. But when you have it and you say it's 1 and it transmits as 1, and that's how the system is now set up and operated in a digital space, there's minimal error and loss within information transfer. When we had that analog wave function, again, there was, you could transmit more information more efficiently, but there is a lot more noise in that, and that's that quantization space here. Now, finance has intentionally, went to the process of they've over quantized, in my opinion, where now we have like a monthly value or you have like an annual income. It is hard to actually judge the risk of a loan of, is it going to default this month? Is it going to default this day, this week? We don't really see that, understand that, because we just kind of aggregate and do the quantization process, and the data becomes, too high level, and we're lacking all the detail and depth in that. So in this chart that I have, I've printed in the paper here, it's figure 1, example of quantization. It's just showing more or less like a smooth line of a signal that we would expect to be transmitted. There's some jaggedness or noise around that. That's part of that process here. And then that quantization noise is just the difference between those. So more or less like we have some sort of error in this process of quantization. In finance, it is much, I'm going to say simpler, easier, because we take a lot of noise within the days, the minutes, the hours, and we just aggregate up to monthly, and bam, we have the value, right? But this is just trying to kind of make that explanation a little bit clearer if you don't come from a physics background, you're not familiar with the idea. So the next part of the paper is going to be on wave-particle duality, and this is really me just kind of explaining that quantization now into a framework of aggregation and simplification. If we move down to figure 2, the blue line on here is just kind of showing the process here of like, this is what more or less like a probability of default on a loan might look like. It might increase and decrease, and then increase a little bit and then decrease a little bit. And now you had these spikes with this. But if we sampled it again at any specific point, so for example, in this, if I sampled it at the green line in this example, that green line would more or less say that that probability of default is much higher. So that consumer, based on the timing of when I maybe sampled throughout the month. So if I'm not summing or aggregating, and some statistics that are used through credit modeling are actually snapshots. If you snapshot this at the top, it's going to look like this consumer has like a 48% probability of default, which is awful. Like, this is not looking like a good loan. But then if you look at the orange line, perhaps you are sampling closer to the payday. The way that you're aggregating the data, the way you're cleaning and processing the data, you end up with this orange line. And again, it looks kind of jagged and kind of bounces around here. And we're going to use this in some sort of linear model like logistic regression, or we could even use it in a decision tree based model like XGBoost. But the values seem fairly close because we're sampling at that periodic monthly value across time here. And again, in this case, it looks like we're averaging out somewhere at like a 13-ish, or 13 to 15-ish probability of default. And again, a 15% probability of default all the way up to a 48% is vastly, vastly different. More realistically, if we were going to be taking the sum of these months, you would have a line that went somewhere through the middle of this wave here, and you'd probably be looking at a 30% probability of default. Now, I would argue from a risk management perspective, we are not truly capturing the probability of default as a more understanding, deeper level insights in this consumer, because there is volatility within that probability that we see, right? If your payment's due today and yesterday you got paid, our probability of you defaulting on that loan is probably very low because you tend to already have cash on hand. And I kind of mentioned this in the paper too, for prime customers that make a lot of money, that have lots of, good credit history, great behavior. Their amplitude on these waves is going to be quite small. Their probability of default might fluctuate a little bit here and there, but not a lot. When we look at consumers that are subprime, we might see huge swings because paydays and timing of paydays is critical. Contract structure, whether they're making monthly payments, semi weekly, I believe, bi-monthly, like every 2 to 3 to 4 weeks, depending on how the structure set up. Like, buy here, pay here, for example, in the auto space gets very, very dicey. And so people start getting creative on ways how to reduce that risk here. This is just a interesting dynamic of this with looking at the wave function. So as we zoom in, loans that were behaving more like a particle now seem to be behaving more like a wave. And it seems like we've just kind of ignored that risk. This is interesting from a finance perspective because when we have looked at things like stocks, for example, you look like mean variance for, doing like Sharpe ratios and whatnot, and Markowitz optimization. We look at the volatility, and we're really concerned with the volatility here. When you aggregate loans on a monthly level, or annual or quarterly or whatever, you get rid of all of that risk, which is really that deviation that we're looking at. We're trying to measure that deviation here inside that loan. So I think we've taken a wrong turn just because data was not as granular as it could be. It needs to be more granular, but we've been waiting for the technologies to get there. And I think now is the time to start to move in the exploration of this research and applications at firms to actually get into the granularities and moving more towards kind of wave modeling here. And then I move on to quantum superposition here. And I know this will seem kind of odd, hand wavy. You can try to simplify it down into traditional probabilities, which is fine. But more or less, the argument from this is that a loan actually sits in multiple states simultaneously until it is measured. So going into physics, with looking at spin, for example, when you measure spin, if it's positive or negative, there are going to be, you're not going to know until you measure what it actually is. Not going to go into the physics realm with this, but a loan can sit in multiple states simultaneously, and it is unknown until we actually measure it. I guess big, market hand waviness of physics would be like Schrodinger's cat, right? You have a cat in a box. We don't know if it's alive or dead until you look in the box. It's the same with the loan here. So imagine you have a consumer, you make a loan. Has that loan defaulted or is it still alive? I don't know. If I go and ask that consumer also does not know. And the reason is because their payment might be coming up in, say, 2 weeks or 3 weeks. And so in their mind, they say, hey, I've got cash. Of course, it's alive. I'm going to make that payment, not a big deal. The payment date of that loan is the date of measurement, okay? So we go and we measure and say, yes, the payment was made or it was not made. The loan is either alive or not alive. So that's kind of the state you can look at. Now, a consumer might also not realize that they're going to get in a car accident in a week and a half and they're going to have to pay for their car. Or they have a medical expense come. Their kid's really sick. They have to go to the ER. They have this huge bill due. All of a sudden, they can't make that loan. The reality is they don't really know where the state of that loan is because they don't know where the state of their financials are going to be in the future at that point of measurement. So they can hypothesize the loan is alive today. And contractually, we would say it's still active. They're still in good standings. They look amazing. But that's because we only care about the monthly date of when we measure that issuance here. And then I point out other kind of examples as well in this paper, looking like at extensions. So maybe you come to the due date, you're like, I'm going to default. I don't have the money. There's nothing I can do about it. Due date comes, you call the financial institution with your loan. They say, hey, that's a really tough situation you're in, medical expense, car breaks down, something happens. Let's give you an extension. So we'll skip this month. Don't worry about the payment. Next month, you can make us that payment. Use your payment more or less that you had this month to fix your car, do your medical expense, whatever, and let's get back on track next month. So a financial institution can actually somewhat revive or change the state of that loan. So that's kind of a tricky piece of this, but essentially a loan through time when we look at it on like nanoseconds or seconds or hours or whatever. And I think we should model these states, as states. I don't think we should combine them together and make some sort of simple prediction of probability of default. I think the states should be separated out, and the modeling of these multi-states should be driven by kind of different factors, because making a payment versus not making a payment, there are going to be very different events, factors, features, behavior, consumer behavior that drive either making a payment or defaulting. Again, we kind of pointed out some rare events here, but they're much more common than people like to admit. And then in the paper, I do make another statement, again, where the quantum mechanic analogy stops here. There are other examples here, like the uncertainty principle, and I had an interesting idea that came through my mind. I don't recall it right now. More or less where when one measure gets more accurate, the other measure gets less accurate. I'm not trying to stretch and make everything fit to this. I don't see any practical applications of this. Quantum entanglement, quantum tunneling. Again, just a disclaimer on the paper, because I don't want people to fully worship and believe and drive down this path when there needs to be more exploration, thought, and kind of a scientific approach of looking at things more objectively. So that was the purpose of putting that in there. And then I have a section on math, or models and math, on how we could potentially apply these in practice here. Quantum superposition. Again, looking at those multi-states here, I break down a real-world example in the paper as well, where we start to think about, and it's later on in an application for retail credit. But here I just kind of provide this example of a general equation. I intentionally made the equations in this paper so general that you could put anything into the equation for a modeling perspective. There are multiple reasons for this. One, if I've done modeling on this, which I do mention in the paper I've done, it's proprietary. So I'm not sharing it. I'm not giving it away. There's no actual information. The equations have been made so general. It's up to you to figure that part out, right? Also, the problem, the applications are all going to be unique. So I would like people to think a little bit more creatively to put these pieces together. But this general credit superposition is more or less you take a probability and the state that it could be in, a loan could be in, and you put these all together, and then it's an additive equation. You add up these probabilities in the states, and you can use these to predict things like cash flow, for example, or probability of defaults if you put them together and you structure the dependent variable in your drivers in the correct manner here. So again, it's just trying to show a rough example of how you would put this together to create a multi-state model. As an example here, as part of the quantum superposition. Now, the wave-particle duality piece is a bit more complicated. Again, I'm just using a general wave function here. This is nothing fancy. I did not invent this equation or anything like that. Again, but it has your x of I in this equation, which is the amplitude of the wave. I'm using sine. And then I have f of x of I, which is going to be some sort of function or variable or value that defines the frequency of that. And then I is going to represent any sort of functions together here. So I am not as naive to say like, oh, it's a magical wave function and it applies to everybody and there is a simple wave and that wave is going to more or less determine every consumer's defaults. No, I do not think that is true. You're going to have multiple waves to capture multiple sets of behaviors, whether you have one for like net income, whether you have one that's like your balance sheet, so you have like your assets minus your liabilities. You're going to have economic drivers and factors as well. So just because a consumer behaves one way in one economic environment, maybe inflation hits like we've seen, tariffs start running in, prices start rising, starting to think about these consumers are going to behave differently. So you need to have economic waves and economic functions to kind of drive and put these pieces together. And I hit that home here with figure 3, which is the general additive wave example, and kind of pointing out like in this example here, the second from the top line looks kind of linear with a little bit of a curve. And the fifth one also has a different curve. If these are economic cycles, like business cycles and wages and inventory and all that, these are going to be very, very slow changing, long moving curves, which are going to look either linear or non-linear, but they need to be added and adjusted into these sorts of equations here. This is just kind of showing in this chart here, the bottom waves, which are all simple waves, can get added up to the top to make some sort of somewhat non-predictable, at least seemingly noisy kind of wave structure here on a consumer's probability of default or, cash flows or whatever you're going to be modeling with this. And then we move on to figure 4 in here, and it's just going to explain more or less, we might put in things that are going to be somewhat deterministic into this modeling framework here. So there's something called more or less like the loss curve or a probability of default for a consumer here. Typically you see a lot of defaults at the beginning when you have a bunch of loans, and then it spikes, and then it kind of goes down into a tail here. In practice, I do tend to see, though I didn't put it in the paper, there seems to be some waviness within the data I've worked with, I have used on these sorts of curves here. I'm not 100% certain that it is going to be guaranteed a wave, but it seems very likely that that is what's happening. There is some sort of wave behavior and oscillation in these probabilities here. From a business standpoint, it makes sense, right? Consumer gets a loan, they're probably most likely to default on that loan within the first 12, 24, 18 months, just because it's a new debt burden that they have. Typically when a consumer makes payments for like 2 years or more, for example, 24 months, it seems they got it dialed in, right? There's usually not that many things that make them default. And so that probability actually drops with that. And so when we look at that across time, again, those in the tail that might be towards the end date of that loan, if they default like 2 months before their final payment, it's probably because a life event or shock or economic driver that's causing that. So again, I think we do see some of these oscillations throughout when we start to zoom in more closely on like more granular than monthly, so like weekly, hourly, daily, nanosecondly, everything like that. But this is an example how you could put more or less a loss curve, a smoother one, into your modeling function, and then you can look at consumer behaviors across time, and then you can actually add these wave functions together to get something that looks more like the blue line in this example here, or maybe the orange line, depending how you're going to model this. But it kind of gives you a little bit of understanding of, we could still see what we expect on a monthly level, but we might see a little bit of oscillation in the time periods between that. And then finally in the paper, I do have an actual application of this. Again, it is generalized to the point that it's hard to understand what I'm actually doing. I apologize, I'm sorry for that. But there are some proprietary pieces in here within Agora Data. So thank you, Agora Data, for sponsoring the paper, paying me to do research at Agora Data. This is just a generalized example. I'm kind of showing that in this case, there's some modeling. Let's pretend there's 3 different states. There's charge off, there's payment, there's uneven payment. We can model these out and have more or less wave functions within this process here. Now, I did not intentionally build wave functions into this, so this model does not have any actual wave functions in it. But this is just going to be the superposition model applied to credit here. So there are 3 states in this example. You could have 4 states, 5 states, 6 states, depending how you define and set up the different states. You could have like delinquency states. So ever 30 days past due on your loan, they're a month behind, then 60 days, 90 days, and 120 is typically considered charge off. You could have those states plus an active state. So you can make this a lot more complex, just to give you a little bit of insight on it. But when you do this, you can have a generalized system where loans are sitting in this superposition of multi-states. You model the probabilities across time, and then you simply apply these probabilities such that you have charts. So for example, figure 5 is just showing these states and probabilities all adding up to 1 with 3 different states here. Our blue state is our charge off. It is cumulative, right? So once you charge off, you charge off. But if you live in a multi-state universe here, when we think this loan sits in multiple states, there's also a probability, if you have not measured, more or less where you are sitting in a different state like full payment or an uneven payment state here. Again, when we model these from a modeling stance, right, I don't know the outcome. I don't know what's going to happen to that loan. So I have to model this as the loan is sitting in all 3 of these states simultaneously across the entire life of the loan here. Now, mathematically, we also set it up so it auto-scaled and adjusted probabilities for the correct probability space. So you'll notice, for example, like loan 0 goes out to about 43 months. Loan 1, which is in the top middle here, goes out to 12 months, right? Very different risk structures, very different designs, right, how it's getting put together. But it's one equation. It's one equation that's just making some sorts of adjustments here. And it's modeling these loans out in a superposition here with 3 different states. And then the final chart here is going to be understanding the actual loan performance on a loan level setup versus what happens, what comes out of a model such as this in superposition here. So in figure 6, it's going to be cash predictions, it's going to be probability predictions as well. They link quite closely. The blue line is going to show we expect to get more or less a lot of payment from this customer. I believe this contract is like $550. Yeah, payment is $550 for this contract. You'll see a consumer never makes the full payment in the model. Because you are always in multi-states. There's always a probability that you are in a charged off defaulted state, which is a bad state. There's also probability you're in an uneven payment state, meaning that you didn't pay the full amount, maybe you overpaid. These all get weighted into this superposition prediction of this loan here. The purpose of this chart is to show, with the different colors here, what would happen in real life in practice, okay? And trying to understand why measuring accuracy is actually challenging in practice and typically not done very well. But for example, the yellow loan, I think that's like let's say period 4. Essentially, a consumer made 4 payments and then it defaulted and it goes to 0, and you collect $0 in that contract the remainder of the life. A green one is a loan that went out to probably about 11. Red went out to 26. The purple line went out to, I don't know, like say 42, 43. And the brown line is somebody made it all the way to like 66 months on book on the 72-month contract and defaulted. You can see from this, though, that having one sample, one loan, is not very good at determining if the model is good or not. When you start to take in more loans, it will start to converge closer and closer to this line here. And with that, I'm going to answer a question from YouTube that somebody asked regarding the paper. They put, I'm trying to understand one of your last statements before the conclusion about how the model underpredicts for the beginning of loan lifetimes and overpredicts for later months on books. For underprediction, is this because the beginning of the lifetime is more volatile because of subprime customers, and especially emphasized then if the sample size of loans is not sufficiently high for your superposition of loan wave functions? For overprediction, is this because the consumers who will default have done so by the later MOBs and only the prime customers have not defaulted and make payments? So what I'm referring to at this is often when you work on teams and analytics teams, they're going to apply a bunch of exclusions to loans and they're going to throw a bunch of stuff out because they're going to classify it as something else. So the model should hypothetically take in every possible scenario. But in practice, you'll see firms that will say, oh, these were fraud, right? The consumer defaulted in the first 4 payments or something. So this yellow line now all of a sudden will disappear from the data, right? And then they'll say, oh, we had, other early payment defaults or servicing issues or something. And they'll start to exclude some of these loans from this practice when they do an analysis. This is often what happens in a business because they're trying to get to what decisions should we make, not how accurate is going to be the modeling. And so what ends up happening is if you notice on this, right, if we had this blue line in the first period and we selected it and said consumers going to make $500 payments, in practice, what's going to happen? You're going to see the brown, the yellow, the green, the red, the purple line. Like almost everybody in this sample here of this 5 loan sample is going to make a payment of $550, which is going to be the contract amount. So what ends up happening is now when you look at this, you go, the model is under predicting, right? This is not a good model. We should not be using this model. Now, I will tell you, as I mentioned, in practice, this typically happens because a lot of early payment defaults get deemed as fraud and get thrown out of analysis. So in practice, if you made enough loans, you should hypothetically collect about $500. That is if a loan is sitting in all the states, the modeling is done correct, the probabilities are set correct. There's a bunch of assumptions on the model development as well that go into this. So you have to review the model to make sure the model is done correctly. And so in the beginning months of this, you tend to see the model is going to be under predicting, especially when you have smaller data sizes. There are very, very, very few firms that get enough loans through the door on a volume level to be able to move this. Now, I worked for a company that ran 10% of the automotive market on loan originations. So we would be much closer to this blue line in practice and it would make much more sense. But for many, many firms, regional banks even, for example, aren't going to generate the volume necessary to be able to hit this. I can tell you, for example, like credit unions are going to come nowhere near this. So they're going to look at a model like this and the business assumption will be the model is under predicting cash, especially for newer firms when they start to get going and they don't have as much data. They're going to look at this and think like this model is awful. It's going to be under predicting. It's not great. Now, if they stick with this model and they stick with it to the very end, they're going to see now all of a sudden what they feel is the opposite. Now, what is happening in practice versus what's happening on an accounting level is different. So the probabilities themselves, the alignments, the modeling can be accurate. However, the way the business feels this is the opposite. So when you get towards the end of that, all of a sudden the model is saying, hey, these loans should be generating $100 in cash. When you look at all your loans, you're looking at it like we got a bunch of loans that defaulted, they're not paying anything. So the model's over predicting now. The model's predicting all this extra cash, but more or less all these loans defaulted. Like I'm looking at this like at month, I don't say like 50 or 60. Every loan in this example defaulted but the brown one. So, is it accurate? Is it not accurate? Like, I don't know. And there's a lot of this kind of political back and forth of how the business feels the model in practice. Now, even when we predict probability of defaults in a standard loan setting with, for example, logistic regression, everybody agrees on the methodology, the variables went into the model. It's predicting something that you do not see because it actually is predicting a probability which is unknown. So a consumer is either active, which is 0, it has not defaulted, or 1, the event of default has occurred, it's bad. So when we predict a probability, right, it's either 0 or 1. It cannot be in the middle. But when we're predicting probabilities, we are essentially looking at it somewhat from this state. But this example and this modeling methodology takes us to another level by trying to separate out the pieces and model them and looking at multi-states for these loans instead of just looking at a binary 0, 1 here. So, and you can get into fractional logistic regression. I've seen people use that as well. You want to get into multi-states. But again, I'd go back to the data granularity piece and argue that with more granular data, this will give you a much more accurate pricing paradigm here. Again, in this example, it's just superpositioning. I believe if we add in the wave modeling, if I had more data, more granular data, there are still limitations even within the current data sources available. If we can get to that state, I think you could add in the wave modeling here and you could actually increase the true accuracy even further here. Now, the way to think about this from a business standpoint is if you take all of your loans, all of your data, and you try to control for the fact that there is going to be servicing bias. So in loan pricing realm. Depending how you service your loans will impact the actual performance of the loan. So when you build a model that has a bunch of assumptions and states, depending on the time frame of your data, if somebody decides they're going to call all of our consumers every single day and people are getting really annoyed and irritated, they're probably not going to make the payments. If you make the calls and they seem convenient and you're easy to work with, you might get payments and customers that will roll back and will not actually default. So the model will seem like it's performing better or worse depending on how the your operations department is servicing. Also, you might have departments that just call once every month to 2 or 3 months and they never collect the cash either, right? So how you interact with these consumers is going to drive payment behavior, going to drive defaults and that sort of thing. And maybe you try to bake that into this modeling framework. I would argue that is impossible to do because the businesses tend to be a little bit erratic in the decision-making process, trying to chase the market and the competition. It's very hard to predict, but keep that in mind when you have these sorts of charts, because in practice, if you could hold all your assumptions constant, you would see somewhat of a blue line. But in applications and using this, you might want to think through if there are any assumptions that you want to kind of adjust or add into your data as you kind of expect your servicing or consumer behavior to kind of change based on the way the company interacts with that consumer. And then in conclusion of this whole video and in this paper in general, I think there are some interesting insights to be gained from this. I think this is a very valid approach. I've seen promising results from this in practice. I will warn, it is very hard to sell people on it, thinking in this weird multi-state thing. A lot of people say, yeah, I agree. It makes sense. I understand it. The waves make sense and everything else. But when you start to get into the applications and usage of these models, it can be a little bit hard to explain and understand why the model is behaving the way it is. There is more nuanced depth and insight to be drawn. I think we can actually understand credit markets, especially retail credit markets, much deeper by doing this, because now we're understanding their daily, hourly behaviors. But in general, right, there's a lot to explore here. I really do hope those of you that are watching and listening, you go out and do some research and drive this further and either prove it or disprove it. I don't really care which direction we go with this, but I think this is a very promising route and a promising modeling methodology to kind of go after and implement into practice. And it might provide you somewhat of an edge in a business stance to beat out competitors. I also hope this will result in more accurate pricing and more fairness for consumers. But in general, I think it's kind of an interesting insight and framework, and I do think it is quite valid and should be explored more. I hope to do research on this in the future, but we will see given data limitations, computation power, and everything else. And I would like to make one final note here, which is quantum computing is much different than traditional computing. I believe we need to move to quantitative modeling in the sense of quantum mechanics, so it is optimized for quantum computing. It is somewhat nonsense to take current problems that are framed in a more traditional, digital framework of 0-1s, do a computation, and then compare that to a quantum computer's computation of the same calculation. It doesn't make a lot of sense because you have different models optimized for different machines. You need quantum machines to more efficiently calculate quantum models. You need traditional machines to more efficiently compute more standard models here. So that I would like to point out as well. I think as we move more down that realm of quantum computing, there needs to be more research like this where we look at things from more of a quantum space and a quantum modeling framework. So anyways, thanks for listening. Thanks for watching. If you found this helpful, don't forget to like, share, and subscribe. The paper is in the description as well if you're interested in reading the entire paper. It is only 14 pages. And as always, until next time.